This is part 2 of our exposition, Waves and Atoms, the Birth of Modern Atomic Theory. In the previous part, we reviewed some of the early models of the atom. We saw that the Bohr model had some deficiencies, particularly it couldn't predict the proper energy level transitions that we were seeing in the various emission spectra. And so we went into the notion of the electron as acting as both wave and particle, and we left off with the notion that the electron is really kind of behaving like a mosquito bug whose path is unpredictable, but whose probability we can determine. So we're considering the electron as a kind of a very, very tiny bug, a particle that we can't know the path of. However, we can get a mathematical equation to describe the probability of finding the electron in any given place. And this equation was worked out by Erwin Schrödinger. This is a 2D chart of the square of his equation if n, the first quantum number, the energy level, is equal to 1. In this case, there is only one allowed probability distribution. And this is shown you in 2 dimensions with a kind of an animation to show that the electron's path is not predictable. The electron probability looks like a cloud of negative electricity. It's not really a cloud. The electron probability, however, kind of looks like one. The spherical cloud is how the electron is going to look on the first energy level, where the first quantum number is a 1. Now, without animation, this is one of the orbitals, electron clouds, on the second energy level. An orbital is a region of space that the electron can occupy. You can see a space here between the areas where the Schrödinger equation, the psi function we call it, psi, is negative or positive. In the area between those two lobes, there is a node, an area where there is no probability of finding the electron. There are more orbitals. In fact, every atom has all the orbitals available to it, although many of them may not be filled or even occupied with electrons. This is one of the 3 p orbitals in the second energy level. So n is 2, and for those of you who understand quantum numbers, L in this case is going to be 1. The gray figure represents the node, the asymptote where the probability of finding the electron is 0. This is another one of the orbitals that's available, but this is on the third energy level, and this is a p orbital on the third energy level. You can see areas of probability here and here that look like those lobes that we associate with a p orbital. And then we have, even inside the node, we have additional probabilities of finding the electron in these p orbitals. And again, the gray figure, there are two nodes here. A node here that goes through the origin and is a planar node, and then a spherical node as well. And this is one of the 5 d orbitals in the third energy level. This is the one that most people find the most fun. And the gray figure again represents nodes where the probability of finding the electron is 0. So again, the different colors that you see here represent the fact that one of these, the psi function, is negative and the other one, the solution, is positive. This is not, however, a cloud. What this is the kind of thing you see in many textbooks. This is a surface of equal probability. So there is an equal probability to every point on this torus surface and these 2 lobes. There's an equal probability of finding the electron at these many millions of points. Next, we can better understand the periodic table now that we know where the electrons are, that is, the probability of finding them in a given place. We can now understand that they're going to be added to electrons in order. That is, the first energy level will be filled first, then the second, and the third, and so forth. And from here now we can study what we call electron configurations, where we start adding the electrons to these orbitals so that they're not just theoretical places where the electrons can be, but they actually have a real probability because there's electrons in those orbitals. Now this is just an idea from Kettering University of how standing waves are created. If two sinusoidal waves having the same frequency and the same amplitude are traveling in opposite directions, here's a wave that's traveling to the right, here's a wave that's traveling to the left. Now you can imagine as these add to each other, when a trough encounters a peak, you'll get a 0 point. And the 0 points tend to stay in the same place. So looking at these things, you see that a 0 point here is where waves are constantly canceling each other out. There you see a peak and a trough and a peak and a trough and a peak. And the same thing is true here. But whereas here we're getting the addition, creating an oscillation that actually is sometimes positive and the other is negative. Now when this is moving at a very high frequency, you will see nothing going on at the nodes here and here and here, but you'll see a kind of a fuzziness here where we talk about probability.